Hey, I'll be talking about work I did last summer at Microsoft. Um, so the key idea here was to try to implement or use ideas from our work on Postgres at MIT uh, to Microsoft, in particular to the Scope database engine at Microsoft. The main idea was that uh, in Postgres with DAO, we saw that if you disable certain rules, it can actually improve the performance of the optimizer in a sort of counterintuitive sense, because it is able to avoid potential pitfalls with by just disabling those rules for particular queries. It's also an approach that is very easily adapted to like a new optimizer, because you just need the hints to disable rules, which made it a good candidate for larger commercial systems. In particular, we wanted to see how this approach would work in a very different environment. There are a lot more rules in scope. The workloads are of a very different kind too. It's a distributed setting, longer jobs, much larger operator trees. Also, in the case of, in the Postgres environment, the rules that we focused on were basically around the join orders, while here there are like a lot more rules with, so one of the goals here was to see that does this idea apply maybe more broadly, or how specific it was to Postgres. So to do this, let's first go over just like a very high level overview of what we are trying to do. So a job in scope is a bunch of SQL queries that are just chained together. It comes in, the optimizer emits out a plan. And we'll use this sort of simple toy model in which let's think of the optimizer transforming each internal state of the query plan using certain rules. Here the colors denote which rule corresponds to which one in this graph. And maybe something like a path through this optimizer leads to like whatever the final query plan is output. And so, you know, our first key contribution was the idea of a rule signature. Conceptually, it is just that among all the rules that are in the system, only some of them would actually be used for a given job to reach the final state of the plan. And so we modified the scope optimizer to keep track of these rules, which we call the rule signature. This has been, this was very useful for us throughout the project. It helped us to find interesting rules. It helped us to find similar jobs, because like rule signatures somehow say something about the jobs as well, that these jobs kind of maybe took similar paths in the optimizer. And was like a clean way to explore a lot of the ideas that heuristics that we were using in this paper. Now, the intuition for what our main idea is that, like, maybe let's say this was the plan that was chosen by the optimizer, and there was this kind of path within the optimizer. And maybe it's bad because it really was due to like some assumptions or cardinalities or something else, that this plan seemed like the cheapest plan to the optimizer. So, you know, you could fix these assumptions, but there can be a lot of these assumptions. It can be pretty hard to fix across the workloads and stuff. The other thing you could do is that you could say something like, well, for this kind of job, it had made similar mistakes in the past. So maybe one way would be just disabling the green rule. It would simply block that bad path and force the optimizer to a different path, which is potentially better. And this is the kind of thing you could learn from repeated patterns in the queries. And you'll see like the rule signature here changes as well, and get this new path within the optimizer. Now, let's go into more specifics, and first we'll focus on exploring the kind of workloads we use, how the rule signatures sort of look like what kind of rules we used. So here we look at one of the three workloads we consider for a bunch of jobs on a single day. Now there's a huge number of potential rule signatures because there are 256 rules. Each rule can be on or off and so on. But what we find is that a lot of jobs actually map to the same rule signatures, like they're almost like a few rule signatures with like 1,000 jobs mapping to them. So it shows kind of there's a lot of structure in these rule signatures, which is somewhat intuitive that similar rules probably, are used together, and when certain rules are used, others aren't used, and so on. But it's just good to verify that we see the sort of standard Zipfian distribution. Now, the next question is when we want to actually run our experiments to compile with these different kinds of rule configurations, by disabling certain rules and so on. Then first we need to choose like which kind of jobs do we want to explore this in, because there are like hundreds or a couple of 100,000 jobs every day over several days that we could look at. So yet for a single day, we see that, there are lots of short jobs, like almost 60,000 here, and there's, half of them are like what we call the longer jobs. Like here we just set the cutoff arbitrarily at 5 minutes. And the key point here is that the longer jobs usually use a lot more resources. Here, since it's a parallel system, we record like the number of containers used for these jobs. So it's most crucial to find improvements on these sort of longer jobs. And so we focus our analysis on this subset of the jobs. In order to further narrow down the sort of set of interesting jobs that we focus on, we sort of look at jobs which run for a long time, but which the cost and the estimated cost from the optimizer is relatively small. Because this suggests that the cost model is kind of wrong. It thought it would run quickly, it really ran wrong. Ran long, and so it suggests that using a different set of rules, we could do better. Now, the next question is, how do we choose an interesting set of rules? Like there are 255 rules, which rules to be disabled for a new job, and so on. Clearly, there's a limit to the number of things we can try, even at Microsoft. So just with the, the computation costs and so on. So the first thing we do is we use the rule signatures along with like various heuristics that are further described in the paper, but they're like fairly straightforward heuristics to understand what are the sort of interesting set of rules for a given job. So like for a given job, you can like, try disabling different rules, see if like, the rule signature changes and so on. And basically we find that, and we further subdivide each rule into like these different categories, like on, or if they're an implementation rule, and this is described further in the paper. But we're sort of trying to divide them into these independent categories, and let's see that within each category, there are only like maybe like 10, 15 rules that can really affect a particular job, instead of like maybe 100 rules. So then, it's already not that large a search space. So, maybe 2 to the 10, 2 to the 15, and so on. And so like, this is something that we don't need to be too clever about exploring. So what we do is that after we use these heuristics and we find this interesting set of rules, we just, generate like 1,000 rules using like these interesting rules. We generate like 1,000 combinations, sets of these rules, and we compile them. So here, we plot out 15 jobs, and when you look at each of the plots, it is a bar plot where each bar represents a different set of rules the query is compiled with. Most of the times we see like the costs are much higher than the default cost, which is in blue. And then there are like a few on the left side, there are these like green bars where the cost is actually lower than the default cost, when we are just using these random, like slightly cleverly generated random rules. This is actually slightly misleading. A lower cost here doesn't mean that the plans are better, because when you uh, when you change the set of rules that are actually used, this actually impacts the cost. For instance, there are rules that impact in which order you compute cardinalities of a few nodes, or how much parallelism to use for a part of the job. And so this would impact the cost itself. So you can't quite compare these costs. But it kind of gives us a heuristic, and we sort of empirically like try some of these like very expensive rules as well, and this is described in the paper. And it's like harder because here we like tried 1,000 different sets of rules for each job. You can't execute all these, like some of these jobs take hours. So we need to select a small number of them to execute. And when we try these really expensive plans, it's often just like it takes much longer, and it's the cost model is usually not so wrong that like the very expensive plans are suddenly like run much faster and so on. But this set of plans, which are like kind of cheaper, they're like interesting because like essentially it's like maybe different assumptions that cost them cheaper, and like if those assumptions were true, maybe they're cheaper and so on. But basically it gives us like sort of the like the heuristic here is just like, okay, we took 10 of these like sort of plans which are like cheaper than the default costs for a set of queries, and we executed them. Recall that like we still don't really have any good evidence that disabling rules for these whole jobs can actually improve the performance. So using all this work, we were trying to find sort of a set of interesting jobs and a set of interesting rule configurations where we hope that maybe it will improve the final runtimes. But so far, we've just described a way to like filter out sort of the interesting sets where we execute like, let's say, 10 such plans, and then we see that in the best case could there be an improvement? And we find that yes, from these 10 configurations, if you choose the best one for each job, then like this is like results from like one of these workloads, but others are presented in the paper. We typically find that can often see like percentage improvements of like up to almost 90%, and like many non-trivial improvements. And then there were cases where like none of the 10 configurations we tried, even when it's like cheaper in the cost model, actually they never lead to improvements or the default case. So I mean, this is already encouraging because it tells us that there exist certain rules that we could disable, certain different sets of rules that we could use to actually improve performance in scope. So in the Bao paper, we've shown that this sort of exists in Postgres with a smaller set of rules, and so like now we know that it also exists in scope. The next thing to do is like because the problem here is that we spend a lot of this time generating candidate rules, then executing a bunch of jobs, and this is expensive. We need to be able to make this decision at compile time. And so to do this, actually, even before that, more than just like runtime improvements, another thing we notice is that the various other metrics that we could care about in scope. And for instance, the CPU time, the IO time, there are other metrics related to how much parallelism or resources it was used, which kind of corresponds to like things like the IO CPU times. And one thing we see is that when we choose, let's say, the best configurations from these like 10 executions that we did with different rules for like getting the best runtimes, it doesn't always lead to the best performance on other metrics, like in the CPU or IO costs here. Like sometimes, we see these like large improvements in terms of runtime, but the IO or CPU costs go up. And this could be because more parallelism was used with this set of rules, and maybe more resources were wasted. And in certain cases, this may not be good. And you know, like say we could also choose the best configurations from these 10 rules for each query for the CPU time. And like now, let's say, for instance, you know, here we see sometimes the runtime is higher or like the IO cost is higher, but the CPU time is like typically, you know, see improvements across the board. And sort of the same thing we see for the IO time as well. And so this presents like an interesting sort of landscape where, you know, we can think of these different metrics. We can talk about which one we want to optimize, and you know, it's like an interesting challenge for the future. But we don't explore this too much beyond sort of these early results in the paper. But we believe that this could be a particularly challenging or interesting scenario in these cloud workloads, where, you know, sometimes rather than the runtimes, you want to like reduce the resource consumption. So like because there are like many tenants or so on. So now, like we, so far we were all doing this scenario in which, you know, we try a whole bunch of potential configurations, execute a lot, and we are seeing like, well, sometimes we can see improvements, but now can we make those decisions at compile time? And so the heuristic here is obvious. If, you know, if you see a similar job in future, just apply the rule configuration that improved runtimes that we saw before. So there are various ways that we can define similar jobs, and this is like sort of an ongoing work that people are still working at Microsoft. Here in this paper, we explore like a simple idea that in a similar job, maybe jobs with the same rule configuration in the future. So this is slightly stronger than, you know, they need to have the same exact template or be from like on the same exact input and so on, because the same rules signature could have jobs with like many templates, maybe multiple input sources as well, and so on. Now, the results we find is that we find cases, which is interesting. We're like, we basically find all these jobs with the same rule signature over a 2 weeks period, and we apply these like the configuration that worked well in like, you know, 2 weeks before on a certain job with the same configuration, and it like works throughout the 2 weeks. Now, of course, this is like rare, because what this is kind of showing is that maybe the workload was really repetitive, and, you know, the same thing simply worked. It's like sort of the ideal scenario. This doesn't usually happen, at least like in the cases we looked at, but it does happen sometime, and, you know, as you can see, it can give you large gains. In the other cases, what we try to do is that we try to find like some of these interesting configurations from like earlier analysis, and then over a 2 week period, we try all of those configurations on like a bunch of jobs. Each of these jobs that are combined together, we group them by like, you know, what their rule signature was, so they're like somewhat similar. And then from these candidate configurations, we have a learned model, try to pick the best one. As we see, we show like, you know, we can often like make like relatively good decisions, and the flat line would be here the default configuration. And like, you know, sometimes you see these regressions in red. You know, it can often make these decisions that lead to like non-trivial percentage improvements for the runtimes. Now, you know, again, this is like very early sort of learning work. There are various like questions about like how, you know, we divide these jobs, and like, you know, and so on. So I want to highlight some of the important like challenges and things that we don't explore too much in this paper. And this sort of learning setup with the job groups based on just these rule signatures is not very scalable. There are lots of rule signatures, as we talk about in the paper and so on. You know, we can only find these improvements in like very repetitive patterns, slightly more broader than just template, same query templates, but, you know, still somewhat restricted. So it would be nice to extend this further. It's also hard to interpret what these like new rule configurations mean, because kind of found those by like trying these random interesting configurations. So maybe interesting to find, for instance, smaller set of rules that is like maybe more humanly interpretable, and so on. It's also disabling certain rules for only like subcomponents of a job. Like right now, we disable them for the whole job, but just that because a job is a bunch of SQL queries, there could be finer grained control that we haven't quite explored yet. And so, yeah, there are many interesting ideas to explore here. And but more broadly, I think one thing this shows us that the ideas used in that aren't just restricted to Postgres or very particularly like just this one like sort of setup, but it can maybe be applied a lot more broadly. Thank you.